first 5G network deployments are based on non-standalone mode, using an LTE carrier as an anchor for the exchange of signaling and control information. 5G is now added utilizing dual connectivity functionality. These 5G connections are today either taking advantage of FR2 millimeter wave frequencies, or for lower frequencies, FR1 frequencies, these are right now only TDD bands. As an example, all network deployments below 8 GHz are using either the N77 or N78 band, in other words, 3.5 GHz, which is only a TDD band. There's no FDD-based 5G network deployments as of the second half of 2019, even if the majority of cellular bands below 7.125 GHz are organized as FDD bands. This is due to the industry still working on the support for FDD for 5G NR. However, these frequencies are already heavily utilized by today's LTE advanced networks, applying features like carrier aggregation to boost the data rates and increase overall system capacity. Due to the spectrum already being in use by LTE, network operators worldwide are facing a dilemma if they would like to deploy a coverage layer for 5G using lower frequency bands. So the question is what to do. Acquiring new spectrum is an alternative, but in most countries not applicable as there is none available. Refarming means opening up LTE frequencies and use them for 5G NR is an option, but this is typically very costly as hardware and software changes are required. The alternative is what the 3GPP standard summarizes under the umbrella NR-LTE coexistence as dynamic spectrum sharing, short DSS. So let's take a look at how this feature is supposed to work. Dynamic spectrum sharing, what is it? So let's take a look at what we have deployed today. I oversimplify the situation in networks, of course, if you're looking at that. Taking an example here with two frequency bands, X and Y, where LTE carriers are deployed, for instance, utilizing different bandwidths. In the example here, 20 megahertz and 5 megahertz. So they're combined over the feature called carrier aggregation. Of course, state of the art today for the operators is the aggregation of 4, 5 carriers in downlink, 3 carriers in uplink as an example. But in order to understand the feature, we of course don't need to do that here with 5 carriers, just sticking to 2. So dynamic spectrum sharing now means the following, that by 2020, the standard has defined 2 different modes. So the one is using this feature in the terms of frequency division multiplex, the other one in time division multiplex. So frequency division multiplex, as you can see here, what we simply do, or the idea is splitting up the spectrum, in the example here with my 20 megahertz carrier, for instance, in 2 times 10 megahertz, where one component or part of that spectrum, 10 megahertz, is still being utilized for LTE, and the other part is then now a newly deployed 5G NR carrier. So this is the FDM approach. The TDM approach, of course, means now that we utilizing the spectrum, but sharing it from a time division perspective. And what I'm showing here is basically now the focus from a downlink perspective. That means we're looking from the downlink side, and the idea is now basically to punch out certain subframes while utilizing the feature called MBSFN, so a multimedia broadcast single frequency networks subframes, which means we empty the LTE subframe, and those empty LTE subframes could now be utilized by 5G NR. So this is the fundamental idea. So basically we're talking about either an adjacent channel approach when we do FDM mode for dynamic spectrum sharing, or a code channel approach when we are doing TDM approach. So, but that is not everything, of course. There's many more fundamental features required to enable dynamic spectrum sharing. The first one I already explained with MBSFN subframe support, but then of course you see here that we need to have certain mapping functionality for the data channel in 5G NR. Certain aspects for the monitoring of the control channel need to be supported, something that is called alternative additional DMRS position, some rate matching capabilities, and also to enable that on the uplink side, an alignment of the channel raster to avoid interference. Of course, we need to take a look at all these features to understand how DSS is working within the 5GNR standard. And from that perspective, let's take a closer look to the individual feature sets enabling DSS. So first of all, the MBSF subframe configuration, it's an LTE feature that needs to be applied to the LTE carrier, defined to enable broadcast over the LTE standard. The relevant information is broadcasted by the LTE network in System Information Block Type 2, where we have an information element called MBSFN subframe configuration. And that information element basically gives me now the allocation or configuration which subframes within the radio frame can be used for broadcast. That was the initial idea. So you see here on my screen basically a full radio frame with 10 subframes, so 10 milliseconds long. Not each and every subframe within the LTE radio frame can be configured to be a broadcast subframe. So for instance, the subframe number 0, number 4, number 5, and number 9 can never be utilized as broadcast. Simple reason is in some of them are synchronization signals being transmitted, primary and secondary synchronization signal, and the others are being utilized for paging. So that leaves us with 6 out of 10 subframes, and now this MBSFN subframe configuration element will exactly tell me the periodicity, the allocation, and in my example you have here the purple ones being configured, and that is of course being signaled to the device as broadcast function in the SIP type 2, as I explained earlier. So now is the question, why are these MBSFN subframes required? Well, we need to enable the 5GNR device to basically synchronize towards the signal, and for that we need to transmit the so-called synchronization signal blocks. So we empty out the LTE subframe. Here in my example, you can see that here highlighted in blue. It's basically the second subframe within an LTE radio frame that is being configured. Of course, by default, we don't want to take away resources from the LTE side significantly, so it's 1 out of 10. So 10% in this example, and it's emptied out. It's becoming an MBSFN subframe, but of course an MBSFN subframe by definition, as it is standardized in LTE release 9, is not completely empty. In fact, it has a so-called non-MBSFN region, which is the beginning of each subframe that could be either 1 or 2 symbols long, so seen here, and this is needed to still transmit the LTE control channel, the PDCCH, the PHIH, and the PCFIH, so significant channels embedded into the overall LTE physical layer structure. And on those 2 symbols, of course, I'm still having the LTE cell-specific reference signals being present. So what you basically see there now, out of the 14 symbols within that subframe, 2 are still occupied by LTE content. So that leaves me with 12 symbols left that I can now transmit in the 5GNR core set, the data channel, and then of course the demodulation reference signals for the data channel. So now looking at that, you see here basically 2 symbols being occupied with the DMRS. That has basically coming with the definition of DMRS in 5GNR, which you can specifically see here, coming out of 38.2.11, the physical layer and modulation specification. And am I having those number of symbols left, then you see basically that my additional DMRS is being transmitted in symbol number 9 out of that subframe. So this is one aspect of DSS, enabling a 5GNR device to sync to the 5GNR signal. Therefore, we need MBSFN subframes. But what are now about transmitting 5GNR in other subframes that are not configured as broadcast channels? So as indicated here, I already mentioned a few of them are needed for synchronization signals, PSS and SSS, and also paging. But what about the other ones that are not configured as MBSFN? Can we use them? And the answer is twofold. Yes, we could, but still the LTE physical layer design gives us a challenge here, and we need to work around